Hello, everyone. Welcome to another episode of Q&A about history of science and technology. And, well, let's see, lots of questions here. Quirius asks, are there exact matches or just similarities between complexity in nature, biology and evolution, society, political, religious, and technology? Interesting question. I've just actually been studying. I sort of surprised myself by coming up with a model for biological evolution, which hopefully I will get to post about in the next few days. Um, but these questions about sort of how evolution happens, and particularly things like natural selection. In other words, what is the sort of variation and selection are two key elements of kind of evolutionary processes, adaptive evolutionary processes like that. It's like you make many possibilities, you pick particular ones, and then you keep going. Given the ones that you have, you make more variations, you pick more, you go and select from that. And it is interesting to see in biological evolution, one kind of has this notion that things get discovered in biological evolution. You know, the concept of a leaf or something, the concept of branching structures, the concept of I don't know, using of eyes, of photosensors, things like that. These things get discovered and then they get built on. And I think it is not totally obvious that one will have a situation where one discovers something and it gets built on, as opposed to one discovers something and one just goes backwards, so to speak. It's sort of like discovering something opens up this new vista of possibilities that then allow one to build on that. It's kind of analogous to, oh, I don't know, in if you're, I mean, there are many different kinds of places where there are many possibilities and you go down a particular path. You're trying to prove a theorem. In mathematics, you can say there are different steps we can take at this stage, and some of them will eventually get to the theorem and others we won't. Chemical synthesis, same kind of thing. You do these chemical operations, you're trying to get to some particular end product, and maybe you'll get there, maybe you won't. You have to pick the particular path. But I think in sort of biology, there's a question of sort of what is the selection mechanism, and in something like technology, it's again, what's the selection mechanism? I mean, it's like products go extinct if nobody buys them. It's a little different, but not so different from organisms go extinct if they don't have enough descendants. Um, my impression is that the phenomenon of sort of evolution by this selection process is robust enough that you will see similarities. I have to say, the things I've done very recently with studying biological evolution, it's something I'd kind of, well, I almost did it like 40 years ago, but didn't figure it out at that time. And then quite by chance, so a few weeks ago, I managed to find some things that sort of have unlocked understanding that. And there's kind of a trade-off between you've got sort of a specification for how to build something, then you follow these kind of rules for building it, and the thing you end up building has sort of lots of complexity that is a result of just sort of the computational irreducibility of following those rules. So, okay, so maybe said a different way. When you look at a thing that has been sort of adaptively evolved and it's complicated, question is, why is it complicated? Is it complicated because it's been gradually tweaked through this sort of adaptive evolution process, or is it complicated because the dynamics of it growing from its rules typically leads to it looking complicated? So actually, it's sort of an interesting question, because in engineered technology, it really tends to be the case that, one's gradually tweaking the thing in a way that one can foresee what those tweaks are going to do. Whereas in biology, it's more you change the genes and then the thing will go through some different growth process, and that growth process has a certain autonomy to it. It's not like we tweak every single step. It's like we point it in this direction and then it goes and it evolves that way. And it isn't the case that it is that we didn't get to do all the tweaking. We get to point in that direction and then it autonomously builds a bunch of things. So I think in technology, for example, that is less true. It is more the case that one is in a situation where one is sort of progressively tweaking everything. I mean, the same thing is true with, I don't know, the forms that one uses for this or that thing. They're gradually tweaked, or legal kind of contract type things. They're sort of gradually tweaked to deal with different cases. So it's sort of an interesting question to what extent those end up looking the same when it's tweaked with understanding versus change the gene and all sorts of different things happen. And it turns out in that with certain tweakings, you get a successful result, even though you couldn't foresee every detail of the result. When it comes to society, it's another interesting question of sort of the evolution of society. My guess is that that is sort of intermediate between those two cases. I mean, now that I think about it, I think that the sort of technological engineering case is you are much more seeing a reflection of sort of the history of the adaptive process, whereas in biology, you're much more seeing kind of the adaptive process underneath, but then lots of autonomous creation of things by virtue of the actual growth processes. My guess is society is intermediate, that there are things where, okay, you can change the culture, the laws, whatever else, and that to some extent you can sort of foresee what will happen there, but to some extent things will happen that you didn't expect. Interesting question. Very interesting question. Thank you. Let's see. RBS asks, how did the development of atomic theory by scientists such as Democritus, Dalton, and Rutherford influence our understanding of discrete structures and the behavior of matter at the atomic scale? Well, I mean, the history of sort of in antiquity, people were arguing as a sort of philosophical matter, is the world made of discrete things like atoms, or is it all continuous flow, so to speak? And at the time, there wasn't really a clear basis for deciding between those two things. And I'm not even sure people had conceptualized what it would mean to make a sort of experimental determination. It's kind of like we can see it and it's obvious and we can argue for it, but this idea of you do this sort of carefully set up experiment and then you conclude something, that was that was a much later stage phenomenon. Although the idea of kind of the workflow, the logical workflow of kind of you set up a hypothesis, you try and verify or falsify it, that was a much more 1500s type Francis Bacon type story, I think, than that kind of idea of that sort of workflow of you assert something and then you check it experimentally. I don't think that workflow really existed in antiquity. I think it's sort of interesting that in antiquity there were concepts of logic, syllogistic logic and so on. This implies that, all those kinds of things. But nature, I don't think got in that loop. It wasn't a thing where we're sort of betting against nature and trying to establish that by virtue of some experiment and so on. I think that if you ask a question about the relationship between kind of the study of discrete structures at an abstract level, let's say in mathematics, combinatorics, graph theory, things like that, and the relationship of those things to the history of kind of discrete models of the world, well, we can talk about that. I think one notable example is there was a theory that people like Kelvin and Maxwell and so on had in the 1860s, 1870s, about the possibility that there could be atoms that are, maybe it was later than that, or maybe later than that, that what are, if there are atoms, if there are different kinds of chemical elements, it was known there were different kinds of chemical elements. What are they? Maybe the atoms of these different chemicals are different knots in the ether, in the continuous thing that was, at those days in a very Victorian way, the so-called luminiferous ether, the light-carrying ether, the sort of the substance that was supposed to suffuse the universe and be the thing which was the analog for light of the air transmitting sound and so on. So, I mean, it is sort of ironic that the ether was kind of, people said, oh, there isn't an ether, because in 1900, the Michelson-Morley experiment got done to do with whether there was an ether drift, whether there was a difference in the speed of propagation of light in different directions as the Earth goes around the sun and so on. And no such thing was found. And so people said, oh, well, there isn't anything like that. And then relativity came along and people said there's no preferred reference frame in the universe. It doesn't matter what your absolute speed is. What all that matters is the relative speed of things. And that was sort of what became the physics textbook story. Of course, in modern times, we know that the universe does have a definite sort of center of mass. The cosmic microwave background defines essentially a center of mass frame for the universe. The Earth is moving at about 1,000th of the speed of light with respect to that. And also, as we start thinking about kind of the actual how space is knitted together, for example, in our models of physics, we get to again see that there is, in some sense, a definite rest frame of the universe, so to speak. It doesn't mean that most phenomena that we experience indeed have the feature that they have relativistic invariance. They are independent of the absolute frame in which one is, but nevertheless there is a small effect of that. But in any case, back to knots in the ether. So that was a thing where that was kind of discrete mathematics of what knots could you make, and there was sort of a hypothesis. Maybe the elements we know, whatever there were, 80 something at the time, maybe the elements that we know are precisely the distinct knots that you can make. And Maxwell and Kelvin both had knew a chap called Peter Guthrie Tait, who was a natural scientist and mathematician in Scotland, and I think he'd been a childhood friend of Maxwell's. But in any case, he ended up being the person who tried to enumerate knots. Say, when are two knots? What are the distinct knots? You can clearly arrange the string in different ways in space, but somehow they're equivalent. They're topologically equivalent knots. A trefoil knot, a knot with a 4-1 knot, a 4-2 knot, et cetera, et cetera, et cetera. These are knots that are sort of correspond to a certain number of crossings and so on. What it means to have a crossing, it depends on how you project the knot. Let's not get into knot theory in detail here. But with respect to this question, it is true that knot theory was kind of born out of as it turned out, not quite correct theory of atomic sort of theory of matter. I think in terms of other kind of discrete mathy things, I suppose, whenever you're doing stoichiometry and you're trying to match up, this amount of this chemical with that amount of that chemical and so on, ultimately those are equations involving linear equations involving integers and trying to match up those integer equations. That's so-called Diophantine equations studied by Diophantus in the second century AD. But I don't think people formulated, when people like Dalton were talking about kind of chemistry in terms of atoms and matching up numbers of atoms and reactions and so on. I think that oh yes, you can get out this power tool of Diophantine equations. I don't think that was really a thing. I mean, I think people from school children on, so to speak, have been doing sort of by hand, can you puzzle through the stoichiometry of, oh, we need 7 of this molecule and 3 of that molecule and so on. I know when we've done these things for Wolfram Alpha and for Wolfram Language now, the way we do stoichiometry is just with a power tool of just using the general Diophantine equation solving techniques that we have to just say, well, that's the answer. So that's a case there. Yeah, a few comments. So I would say that the history of kind of knowing that matter is discrete is, I don't think Democritus and the Epicureans and folks in antiquity, beyond just philosophically saying, oh, and matter is discrete, I don't think they had much in detail to predict or say about how matter would work. Certainly things like the kinetic theory of gases, the idea that a gas was made of discrete things, that had sort of some premonitions in the 1600s, but it really didn't get serious until, the 1800s and so on. That was people didn't understand the idea that, yes, you could actually make a gas out of things bouncing around, and that was how you got pressure in air. Robert Boyle in the mid-1600s, I think, had studied kind of the pressure of air And he had these different theories about what air was. How would there be spring? He called it the spring of the air. What was it? He talked about maybe it was like there was the content of the air was like a set of microscopic kind of things that were like a fleece of wool. I don't know quite, which you can have some wool and you squash it and it's only somewhat squashable. And he had other kinds of ideas that they were sort of things twirling around each other, like Descartes had his sort of vortex model of the world. But it wasn't for another 150 years that it really became established that those were discrete molecules bouncing around. I think when it comes to Dalton, I don't know that history as well as I probably should, but quite a lot of what was done in chemistry was just sort of counting. Oh, this reaction happens, that reaction happens, this amount of this gas is produced. We can make that all match up if we assume that there are molecules where there are certain numbers of atoms with chemical formulas and so on. And it was kind of a numerology type story. It's sort of interesting that when that came about later on, when lots of particles were being discovered in the late 1950s, early 1960s, all these particles being discovered in particle accelerators, and there were all these sort of ideas for what these particles might be. First they were discovered in cosmic rays, then in particle accelerators. There's protons and neutrons, but then there's lambda particles and sigma hyperons and psi cascade hyperons and all kinds of other things. And there's just this sort of complicated zoo of particles. And at first, the kind of understanding why there was this complicated zoo was done very much in terms of group theory and in terms of very abstract mathematics. It's kind of like, well, just as you can say we can take this thing and sort of rotate it, and we've got, an icosahedron or something, and it has certain symmetry where the icosahedron looks the same when we rotate it this way and that way. People sort of imagined there was some kind of internal degree of freedom that you could sort of rotate to get from a proton to a neutron to a sigma particle, et cetera, et cetera, et cetera. And it was really analyzed in a very theoretical, mathematical way that looked very kind of non-mechanical until 1964 or so, when Murray Gell-Mann and George Zweig and so on, and it kind of came up with this idea of quarks. And where we could just say, okay, a proton is two up quarks and a down quark. A sigma particle is a sigma plus will be a strange quark, an up quark, and an up quark. And then it became rather straightforward to just sort of numerologically say, oh, there must be these particles and not those. And Murray Gell-Mann famously predicted the omega minus particle, three strange quarks altogether, a charge. Let's see, that would be it's charge -1. That's right. Strangeness 2, strangeness 3 particle. That was duly observed, I think, in 1968 in a particle accelerator, I think Brookhaven National Lab. The little track of an omega minus decaying into a psi particle and so on was observed. It was a great sort of triumph of, well, particularly the quark model, of being able to predict, yes, there will be this thing. By the way, that idea that there would be that thing, I think, was much less clear when it was couched in terms of group theory and so on than when it was couched in terms of just add up these quarks as discrete things. But so that was a case where what came first was the abstract group theory. What came later was just the counting type argument. I think it's worth remembering that discrete mathematics was not a particularly significant area of mathematics for the first part of the 20th century. Combinatorics was, it had come about. People like the Bernoullis had thought about it in terms of the theory of games in the 1600s, 1700s. There were sort of isolated pieces like, Euler, 1700s, sort of invented graph theory for solving this problem of the afternoon strolls over the bridges of the city of Königsberg, and this question of could you kind of have a path where you go over all the bridges without crossing any bridge more than once? And that turned into so-called Euler circuit for a graph. And he kind of idealized the bridges of Königsberg into this abstract graph. But they were isolated examples of things like this. The real sort of enthusiastic interest in discrete mathematics didn't develop until really way into the kind of computer period. A lot of discrete mathematics had also shown up in kind of recreational mathematics. Again, that was somewhat separated from the mainstream of mathematics with its emphasis on algebra and geometry and so on. I suppose another sort of place where discrete mathematics had entered sort of a back doorway was in mathematical logic, where it was sort of an attempt to mathematicize, to take kind of the logic that had come from Aristotle through Boole in the 1800s and been sort of mathematicized, but to sort of build on that amounted to discrete mathematics, although it wasn't really talked about in those terms. And certainly the power tools of discrete mathematics were not used there. So a few thoughts about that. So question here from Kathy: how do historians know with certainty the identities of prominent historical figures? Could there have been more to the Socrates, Plato, Aristotle timeline? I think absolutely. I think that, the way that the memory of people and their works and so on gets preserved over the course of millennia is very messy, very arbitrary. I mean, Aristotle was really sort of lucky that his works were picked up by Aquinas and, really promoted that way. Otherwise, Aristotle would not be nearly as famous. If the Catholic Church and so on had not picked up Aristotle through Aquinas and such like, had not picked up Aristotle as kind of well, not quite a patron saint, but sort of a key originator of kind of ideas about how to think about the world, I don't think Aristotle would have had nearly the reach that Aristotle had. I think it's always funny when people say, "Oh, this is a bust of so and so." Well, sometimes it is, and sometimes it isn't. Sometimes it's something that was made long after the fact. I mean, kings and such like had the advantage that they often got their image, presumably accurate image, on coins, and there were lots of coins, or maybe they also got their image on some grand monument that was built that survived. But coins are a really good bet because there are just lots of them. And so, somewhere there's going to be a picture of Alexander the Great because he was on a coin. So, that becomes a clear sort of that's distributed. You think about, I don't know, the blockchain pitch of, distributed ledgers and so on. When you have coins and you've got lots and lots of coins distributed all over the place, that's a way that sort of you're going to survive in some form or another. I think that the question of kind of a thing that people would often do is they would comment on other people's work. So, for example, Democritus, we just mentioned, very little of his work, essentially none of his work, except for aphorisms, survives, because the only thing that's survived is things that other people quoted from him. So one kind of knows he existed. Now, there are even more confusing things because there are people who have the same name, like Euclid. There are many Euclids in antiquity. But was it the same Euclid? Was it a different Euclid? One gets confused. I mean, I know even in much more recent times, the Sadi Carnot, the person who first sort of started talking about the second law of thermodynamics in 1824 or so, he had a cousin also named Sadi Carnot, who became president of France in the later 1800s. And I was looking at a thermodynamics textbook recently, and by golly, they have a picture of the wrong Sadi Carnot there. So even in recent times with, expensive, college textbooks and so on, these things, it's like, well, that isn't really a bust of Socrates. It was somebody completely different who maybe even had the name Socrates, but was not the Socrates who we know. So things can get very, very confused. I think there are sort of rare moments when there is clarity because something gets discovered. I mean, right now there's this lovely project to try and recover these scrolls that were kind of carbonized in the eruption of Vesuvius in 79 AD, that were kind of buried in this library that had originally been probably owned by Julius Caesar's father-in-law, who happened to be an enthusiast of Epicurean philosophy. And so it's quite possible there might be 10,000 scrolls, and if all the fancy kind of CT scanning and machine learning techniques work out, it'll be possible to read those scrolls, and maybe that will contain the complete works of Democritus, which we thought were completely lost. I mean, there has been many times there have been situations where people, it's like, oh yeah, that was mentioned, but we don't have anything from that. And then subsequently it got discovered. I think it was even true that the works of Cicero, for example, were thought to have been completely lost until they were found in some random corner at the Vatican Library at some point. And I think in one of the things that is funny and confusing about history from antiquity is what was kind of mythical and what was real. People thought the city of Troy, for example, wasn't a real thing. They thought it was just a story, so to speak. And then I guess Schliemann in the late 1800s found the city of Troy. He was an archaeologist, German semi-amateur archaeologist, I suppose. Famously, Troy, like many archaeological sites, is in many, many layers. And famously, there was sort of a question of what is the Homeric Troy? And Schliemann used dynamite to blast. Yeah, I think dynamite existed by then. Am I getting that historically right? Maybe it was gunpowder. To blast through the layers that he thought were irrelevant layers, trying to get to Homeric Troy. And he almost certainly blasted through the layer that actually was Homeric Troy. Sort of a lesson for be careful when you do archaeology. But in any case, I think, I'm quite certain that there were more people involved and there were people we've never heard of. And, if you look at even modern times, there are plenty of situations where, it's a complicated thing. People can be very famous contemporaneously and completely lost to history. And sometimes, in some sense, deservedly so, sometimes not. Sometimes there are people who are not famous in their time, and then subsequently they become super famous. Alan Turing is a reasonable example of that. He was not particularly famous in his time. Even when I first heard about him in the 1970s, 60s or 70s, he wasn't a famous person at that time. He was just, Turing machines were known in theoretical computer science, but the whole sort of, not quite a myth, but the whole story of Alan Turing wasn't a prominent story. Many people, in their, often ideas that in their time, people were like, oh, I don't know, we don't really care. And then subsequently people realize that was a really good idea, but it took another 100 years or more for the world to get to the point where people realize, yes, that really was a good idea. And then when it's rediscovered, there's the question of, does that rediscovery connect back to the originator? For example, Mendel in the discovery of kind of Mendelian inheritance in the 1860s and so on, that was kind of completely lost and then reappeared in the beginning of the 1900s, but it was connected to Mendel. It might not have been. It might have been, Thomas Hunt Morgan, who was the person who did sort of corresponding things with fruit flies in a more elaborate way. It might have been that was the inheritance we heard about, and Mendelian, Mendel was, oh yeah, there was this monk, and one doesn't really know much about him. So these things go in all sorts of different ways. I think it's all sorts of things that get named after people were not invented by them. I mean, Fibonacci numbers were certainly not invented by Leonardo Fibonacci. He popularized them, and I think it's sort of interesting to extrapolate people where one says, oh yeah, that's a well-known person who's writing all kinds of I don't know, books and so on today. And there are cases where I think I can say, in some time in the future, nobody will have heard of that person. And because I've seen the same kinds of things from the 1800s and so on of, oh yes, there was this person who was making a lot of noise and writing a lot of popular books. And then turns out they didn't have really hard surviving content. And so it's just not really remembered unless there's another reason to remember that particular person and their contribution. So I think there's a lot of kind of, there's a lot where there's many aspects of luck. Also, the luck of whether the manuscript was preserved, whether the person who wrote in some language that people didn't really read very much was completely forgotten for this or that reason. So I'm quite sure that there was a lot more detail there that we don't know, and some of it may be important in terms of the history of ideas, and some of it may be more promotion of the time and not particularly important in terms of the history of ideas. Oh gosh, many questions here. David Brown asks, do the majority of historians of physics now have a favorable opinion of string theory? Oh, I don't know. String theory, maybe I've talked about this in other times, but string theory is a weird case. It's kind of what is it? A used theory, a third-hand theory or something. Originally, string theory was developed as a theory of strong interactions, and back around well, it sort of emerged. It was in the beginning of the 1960s originally, and then it kind of reemerged another time, and then reemerged another time, and it's been kind of what do you call it? I mean, a regifted, not quite regifted. It's kind of one of these things that's a thing that's been kind of reapplied for a different purpose multiple times. I think that it is something which has been an interesting driver of mathematical physics. It's not something that people say, wow, string theory, they really nailed it. That's how the world actually works. That I don't think anybody would say at this point. It's a contributing piece of a development of mathematical physics, which also, by the way, dovetails very nicely with our physics project. But I don't think I think, will it be seen as an important building block? I'm not sure. I have to say, I would say I'm not sold on that right now, although it has led to rather circuitously to some other things which are probably more important building blocks. Boy, oh boy, boy, there's questions about history of mathematics here. Let me see what else there is here. Gosh, many interesting questions here. All right, Golagaz asks, is there any scientific reason that pure mathematics concepts are picked up by physics much later? It's really a question of how good are those mathematicians at figuring out what sort of the obvious abstract structures are. And then it's a question of, given that you have a hammer, that in terms of certain pure mathematical concepts, is physics just finding the nails, so to speak? In other words, there are things that we can now think about in physics, even using things that I've developed, that we couldn't really think about before in sort of precise terms. There are things that are different from the things you can think about using traditional, let's say, calculus and so on. And that sort of expands what physics might consider to be its domain. So there's one thing is, we're given calculus. What can you do with calculus? Oh, you can analyze fluid dynamics, you can analyze this, you can analyze that. You can't probably analyze fluid turbulence very well that way. But given some tooling from mathematics, what can you do? That's one thing. The other thing is, does mathematics introduce sort of ideas that are somehow the obvious development of abstract formalism? So there are examples that go both ways. I mean, a classic example which went in kind of a not so obviously useful is transfinite numbers and so on. The idea from Georg Cantor in the 1880s, 1890s of kind of maybe 1870s actually, sometime around then, of sort of, you get to infinity. There isn't just one infinity, but there's this whole giant world of different kinds of infinities. And it's something that is mathematically interesting. It was an important driver for set theory, which Cantor also invented. But it's been a thing which hasn't really had uses in natural science, for instance. I recently encountered a kind of place where it seemed like it might really finally be useful. But it's something which was kind of built out by mathematics, quite independent of its application. Another area where one could say that was mathematical logic. One could say, where's the natural science application of mathematical logic? And mathematical logic is what sort of eventually gave us computation theory. And again, where's the natural science application of that? That was kind of, I suppose, my contribution in the 1980s was sort of making the connecting these kinds of computational ideas with ideas relevant for natural science. So it took a long time. That wasn't an obvious, oh, now we have Turing machines. Okay, that's relevant to natural science. That was, well, you know, I was deeply in the middle of that particular one. So this, I mean, people, you know, Eugene Wigner, for example, had this paper, The Unreasonable Effectiveness of Mathematics and Physics. I've always thought that paper was kind of a put-up job in the sense that it is a large part of it is that which we can analyze is what we study in physics, and that which we can analyze is what we have been provided with the mathematics for. And so there are other cases where the sort of does the physics end up being the driver? I mean, I was just mentioning group theory in physics. Group theory existed from the 1830s. It was applied in physics in, well, in the kind of 1940s, 50s, and so on, first to atomic spectroscopy and then to particle physics. So it was a kind of already existed in mathematics kind of thing. Now, once these things sort of, quotes, exist in mathematics and are brought into physics, they often greatly deepen as they are used in physics and other areas of natural science. It's kind of like they get streamlined, they get the different cases get studied, and the whole thing. And it also, you have kind of a concrete anchoring for these, what would otherwise be quite hard to understand abstract ideas. I think so that's I mean, having said that, there are also places where, particularly in more modern times, where physics has been very much sort of the driver of mathematical development. That was during gauge theories, the development of a bunch of kind of algebraic topology, differential geometry kinds of things in the 1980s and so on, was sort of driven by the desire to understand gauge theories, which were an idea from physics, better. And that happens. And I think that's, and it's to some extent, it's an interesting question whether it's happened from areas other than physics. I think from computer science, a little bit. I mean, certainly some things about asymptotic behavior of recurrence relations, things like that. It's a fairly specialized thing. I'm a little bit hard pressed to think of places where sort of the pure mathematics has been driven by maybe I'm missing some big area there. I mean, certainly there are many, many detailed things where the application in computer science has forced sort of a streamlining of the thinking in pure mathematics. And biology is another case where sort of there are the beginnings and hints of things where this is a thing that's important for biology, and it sort of drives the development of that in mathematics, but it hasn't happened in as large scale a way as it's happened from physics. I mean, obviously the invention of calculus by Newton, at least, different from Leibniz's invention of calculus, but the invention of calculus by Newton was very much driven by the desire to solve a physics problem, things about motion of comets and things like that. Let's see. Giovanni says, do you find it odd of a lack of human history, considering how long we have lived on this planet? So I think what you might mean is that we don't have as many records of what happened in the past as we might have. I think, you know, our species invented language, you know, a few 100,000 years ago, presumably our species, I don't know, species close to us at least. And, you know, language is the key thing for sort of communicating kind of ideas, not just here I am, I've been fossilized, but kind of, you know, ideas, concepts, stories to future generations. I mean, at some level, we have very distant history from, you know, we find a whole crowd of trilobites. They were hanging out together when they got fossilized. And there's probably a whole story about, you know, afternoon in the park for the trilobite families. And then they got fossilized. And, you know, 400 million years later, we pick them up and we can see what was going on there. I think but this, and by the way, in more recent times, there are, cave paintings from what, a couple of 100,000 years, 100,000 years ago, at least. And sometimes we can recognize, oh yes, that's representational art. There's a picture of a bison or something. And sometimes we're like, well, there's a bunch of handprints, or there's a geometrical-ish pattern, and we have no idea what it meant. And perhaps, somebody could come along from that time and say, oh yes, that those collection of handprints, though a reminder of this great story that was being told about what happened to, our distant ancestors in this or that place. But we don't recognize that. So I think kind of the thread of human history that we do recognize has to come from linguistic representations, largely. An interesting question is, if you think about more pictorial representations, I don't know, I'm thinking of the Bayeux tapestry that celebrated the Norman conquest of England in 1066 or whatever. It's a kind of a comic strip. And I don't know, if there wasn't ambient history, whether we would know sort of what this comic strip meant. Or whether we would just be like, what's that dot there? Oh, it's a comet. Well, we didn't know that because, we can kind of guess what it is, and we'd be stuck, almost trying to guess the cave painting handprints. But so, I think that history tends to come from, that we know in detail, comes from this thread where it is written in a language which ultimately we can understand and translate, and where we can sort of translate those thoughts into current thoughts. I mean, I don't think if we knew, you go to an archaeological site and you say, what was that structure for? Nobody knows. They might say it was for ceremonial purposes, which means, people did something there and we don't really understand what it was. And so similarly, I think, it's an interesting question whether at what point in history kind of the issues were similar enough that we would sort of understand a description of what was going on. I mean, for instance, it could be that there was some elaborate, what we would now call ritual event, where everybody came and, I don't know, sort of, waved their arms around in a particular way. And you'd say, well, we might just describe that as, religious ceremony or something. But that might have been, something which was a reminder of the epic of so-and-so from whatever time. And we don't know that. And we don't have that sort of thread of cultural connection to be able to understand that. I think is also a question, if we go really far back and we ask kind of, what did the language represent? So it's kind of like with babies, for instance. It's like they make various noises, they say various things, and it's like, what does this mean? Does it have a meaning that we can, does it even form, have they even formed what we would consider a thought similar to the thoughts we form when we're older? If not, it's kind of like, what did it mean that the thing, take it also to other animals, what does it mean that, the animal is curious? Is that really a concept? Is it the animal is pondering the future? Who knows? But it may be that thought hasn't really formed, and that may be an issue with human history as well, that things which we would now describe as, oh, they elected a leader. Well, it could be that at some point in the past, everybody was, stamping their feet in some way, and it's like, okay, then Egbert should lead our tribe or whatever. But and in modern terms, we would describe that as they elected Egbert as their leader. But that wouldn't be the kind of the ambient description of the time, but who knows what that would be. And they might not even describe it. Another thing that's always interesting about the progress of things is there are things where nobody really described it. It was just a thing that happened. And then people started being very precise about it and saying, kind of what it was that had happened. I mean, there's a lot of that in descriptions of, I don't know, let's take, I don't know, descriptions of human states. Oh, so-and-so is depressed or whatever. It's like in the past, and that might be a thing that you can sort of define in some clinical way, and it's all very precise. And in the past, it was kind of like, oh yeah, you know, uh, I don't know, some melancholy, whatever it was. It wasn't a definitive. Perhaps not the best example, but it wasn't something where you could put borders around it and start being precise about it in some sense. And I think that's another issue with kind of defining history. It's like, well, this stuff happened. You know, people, you might say, okay, did they have a village? Well, there were people hanging out and they had some sheep and they did this and that and the other. And I don't know whether it was a village or was it a country? You know, we try and draw country borders in Wolfram language for our knowledge base going back into distant past. And sometimes it's just, well, it's kind of a circle because we don't really know what it was. It wasn't really defined. There was no, yeah, the country is a good example because that's something where at some point in history, probably after the 1700s and beyond, it became more precise. There were passports. There were, you know, border control. There was you know, you know, there was at least there was some kind of fence or something. Well, maybe there isn't in some places, but there was some notion of a precise definition of a border between countries, as opposed to just, yeah, well, on that side of the river it's this and that side is that, and oh yeah, this piece that's sticking into the river, we don't really know whose that is. So, you know, things become much more precise and we can start saying, you know, there was a war between this country and that country. But when it was all very amorphous and they were just kind of people hanging around and tending sheep and wandering from one place to another, you couldn't really say that. And so it was kind of like the baby version of describing reality. You couldn't really nail down something where you could really talk about it. Um, Let's see. Eli comments, with respect to notable people in history, humans seem to be completely obsessed with credit for their contributions. An interesting feature of human ego, Taoist philosophy believes the Tao makes achievements and lays no claim to them. It's interesting. I think that's a very culturally different thing. I mean, I would say even just you know, operationally with different people, some people are very much like, yes, I did that. It's really, you know, it's important that it's a me thing. And other people are like, yeah, it's kind of was fun to do, and I don't really care if anybody knows it was mine. Sometimes it's like if it's software developers, for example, it's like, I don't want people to know it's mine. I mean, then people are going to start calling me up, you know, finding my home phone number and calling me for tech support type thing. So I think it depends sometimes on people's kind of what they see as being central and what they don't see as being central to their own kind of you know, existence and their own character. I mean, there are plenty of things where you know, I mean, I've suggested a huge number of things in my time to different people, and sometimes they flower into grand. If one's lucky, they flower into sort of grand developments. And it's like, look, I just mentioned this thing to somebody at lunch type thing, and you know, that turned into some big thing that gets named after the person I mentioned it to, or whatever else it is. That's you know, I think it's one of these things where if you feel like different people have different points of view, but I kind of tend to feel that if it was sort of a very kind of trivial thing to suggest, it's kind of like whatever, you know, it's part of the general flow of the world. Whereas if it's something where you put, you know, a decade into it and you really, you know, built all those pieces, that's something that I feel like you're more invested in, so to speak. But yes, it is certainly true that the sort of the promotion of the self in terms of, for example, oh look, I did that type thing is complicated and has been different at different times in history for different people in different areas. I mean, in some areas, it's like, oh yeah, you've got to, you know, it's very significant to say this came from this place. Other things, I don't know, like legal documents are a famous example where, you know, people say, well, I need an agreement for this or that thing. Let me look around on the web and find somebody else who has a similar agreement. And you just take a chunk out of that thing and you put a paragraph in there, and it's like, hey, this is my agreement. And you don't say footnote, footnote, footnote. This came from this place, this place, this place. People don't expect that. It's not the same kind of thing as other areas. I mean, another one notable for me is when you make a tool like Wolfram language or Mathematica, and people use it and they produce things with it. There's kind of like, do you attach the tool to what they produced? I kind of made the decision, don't worry about it. maybe the wrong decision. I mean, it's kind of like you might say, well, actually, people should have said, oh, I got it from this tool, rather than it's just this is the symbolic result that is true. It's like I got it from this tool kind of thing. But yeah, I think it's a I mean there when one does history, it is sometimes it's like it's really good when somebody signed what they did because it tells you something about where it came from. It's true in for example Indian history and I think Chinese history as well, particularly Indian. There's a tremendous tendency to just say this is what was written or this is what was said. When was it said? We don't know, within a few hundred years, because nobody put a sort of stamp that said it's this person and this person's connected to this and so on. It's more a society produced this thing, and it then becomes very hard to sort of fit it in a timeline. So from the point of view of future historians, having somebody take responsibility, so to speak, is useful. Whether it's it's a complicated thing, because this whole question of do you is it worthwhile for society? Is it worthwhile for the individual to say, hey, it's cool, I did this? Sometimes it's more important than others. Depends on how people feel about things. For society, is it important to sort of promote the fact that people are going to do sort of significant and singular things? To some societies, traditionally kind of US style society, it's been like, yes, inventors are a good thing. In other places, it's like, no, it's all a collective thing. Let us not kind of present there being unique kind of inventors. It's just like, this is the progress of society. And that's seen to be a better thing to communicate to people. WM asks, can we reconstruct lost works in history using AI through contemporary references and searching for the influence of lost writings had on known writings? It's an interesting idea. I mean, in other words, could we triangulate to know this is what Democritus really wrote? I mean, there's not a huge corpus of other stuff from that time, but right now we've had kind of historians kind of trying to conceptually piece things together, but maybe the LLMs, which are good at sort of doing this sort of general text, not quite statistics, but sort of text interpolation, maybe from the LLMs we'll be able to say kind of, yes, there must be a common source. I mean, I know people did that, oh gosh, eons ago for books of the Bible of, was there a common source to various books in the New Testament, things like this. And I think that was sort of done by textual analysis and so on. And maybe the LLMs will just say, yeah, it's kind of obvious, or not, as the case may be. It's an interesting idea. It's an interesting thing to try to. I mean, people have endlessly, debated whether all the works of Shakespeare are by Shakespeare. They probably are, I would think. Somehow often in history when sometimes there's the weird conspiracy thing that really happened, that was the real thing that happened, where people in the know that that's what happened. And quite often it's not the case. And it's just what you think happened was actually what happened. My guess in that case would be what you think happened is what happened, but who's to know? But that's a case where there's been endless textual analysis, and perhaps LLMs have more to say about that. Let's see. Cliff comments with respect to some previous things I was saying, brings up the point that there were likely many people back there in the past who had amazing ideas that would have important applications today, but they didn't have the good fortune to be noticed and documented. Yeah, that's probably true. I would say that there is certainly a sort of a residue, a percentage where that happened. There are also maybe less than one thinks, because here's one of the things that happens. There is an isolated idea. The idea has no context. that idea cannot grow at that time. Until the context exists, that idea just will not, will not grow. Even if somebody has the best idea in the world, without some degree of context, without sort of fertile soil in which to grow, it really won't grow. I mean, I know that, I've had this experience in my own life that things one invents, when there isn't sort of an ambient understanding, it's just like, even for oneself, but for other people as well, it's like it doesn't catch hold. And it really, it's, it's sort of perhaps personally unfortunate for the usually dead by that time person who had that great idea that was just sort of ignored in its time. I think, but I think it was hopeless. And I think that, with some ideas I've had, for example, I perfectly well know that I have to build a whole city around that idea to be able to have that idea prosper in a serious way. I mean, certainly ideas about sort of computation and its relationship to sort of fundamental science and so on, I've spent a long time building a big city around that idea, so to speak, which has allowed it to get a reasonable amount of traction. But without that, if it was just like, hey, there's this cool idea, I write one 3-page paper about it, it's hopeless. I know that that's hopeless. Ideas have to be sort of buttressed to be able to actually prosper and survive in the world. And I think in terms of and that's certainly true also with inventions as well as with ideas, that there can be an invention. The fax machine was known, that idea existed in the time of telegraphs. I think Gauss had a very primitive fax machine made with telegraph, but it just couldn't sort of get traction in the world until electronics existed, and transmission technology and so on existed that made it really feasible. I mean, same with things like drones and so on. Another example of that, where there had to be just a lot of infrastructure developed with batteries and microprocessors and so on to get to the point where that was possible. Let's see. Well, Kathy asks, how did the concept of zero originate and evolve in mathematical history? It's a good example of something where when things become more precise and streamlined, new ideas have to be introduced. Because the notion of counting 1, 2, 3, okay, that's been presumably known for a really long time in human history. We have tally sticks and so on from tens of thousands of years ago. But negative numbers, for example, the idea that, clearly you can take things away and you can take 5 sheep out of the herd and so on. But the concept that there is a thing you can pick up that's -5, that concept did not really sort of arrive until the 1400s and 1500 actually. And actually, bizarrely, it really arrived in particularly in the work of Cardano, who was working on cubic equations, a fairly obscure corner of mathematics, where he ended up introducing both imaginary numbers and negative numbers. And like, you really need these things. They're really but the fact that imaginary numbers, which are a much more complicated mathematical concept, not taught to people until much later in their kind of mathematical trajectories in modern times, was an idea that sort of came in at the same time that one really realized one really had to be able to pick up a negative number and do things with it. So the idea that zero was a thing worth talking about, I'm sure one can back project to endless pieces of history or things that were written where it's kind of like, well, you could interpret it this way. I think people don't usually interpret the Babylonians as having had a notion of zero. Probably correctly, I don't know. I mean, it's often said that there's Indian mathematics from, well, some amount of time BC, I'm not sure how much, where people say it had a notion of zero. But I don't completely know what that means. Because if there's a piece of poetry that says, and when we have the number three and nothing comes after the number three, and then we still have a number three, you could say, oh, they invented zero, or you could say that's just sort of some poetic flourish, and it isn't really an invention of zero. I think so. I don't really know at what point people had sort of had the need to really sort of say there's zero, it's between, you got to have negative numbers to really care about zero. I think it's worth remembering also that the idea of things like variables, functions, all these things, they mostly came in when things had to be streamlined. Like Newton was, I think, the person who really came up, really codified the idea of variables in the sense that we do them in algebra today. And he needed that because he was building the next stage of calculus, so to speak, beyond algebra. And that's a pretty common thing to see, that when you're building the next stage is when you really codify the previous stage. I've seen that in language design for Wolfram language, for example, that at first you build something that's just sort of one of it, and you do it in a particular way. And then you say, I'm going to build on top of it. You need to make it more solid. You need to make 5 different things that are like that. And then you streamline it and you come up with this new level of abstract concept. And I think that's happened a lot of times in the history of ideas. Let's see. WM asks, do zero and infinity have the same origin? I do not believe so. I believe that the notion of the infinite is again a notion that was surely existed sort of in everyday discourse before it was codified in mathematics. I mean, a notion of the everything, a notion of, God as the limit of sort of greatness, bigness, power, whatever else. That was sort of a place where infinity would enter, where it wasn't mathematicized. It was just and there is the infinite, so to speak. I'm thinking in terms of zero, the Leibniz, for example, I was just reminded of this recently because the Leibniz, who kind of sort of was a big one for talking about binary numbers. Presumably, binary numbers came from China and the East, from the I Ching and things like this. Presumably, Leibniz heard about them from missionaries who'd gone to China and so on, maybe, or maybe he just invented it out of whole cloth. We don't really know. But in any case, he was very keen on the idea of binary numbers as a sort of way of making something from nothing. And he had this medal that he wanted to have struck in his lifetime, but never happened. I finally got that medal made as a kind of a gift to my friend Greg Chaitin a number of years ago. But in any case, the gift, the medal has on it sort of a celebration of binary numbers, and it says something like ex nihilo omnibus with what is it, cum unum or something, omnibus descendit, which would mean from nothing. Oh no, what unum sufficit, I think. One suffices to make everything. So that's sort of a description of binary numbers. You start with zero, you just put ones in along with the zeros, and you can make everything. But now when you read that kind of slogan on the medal, it's like, is this an invention of zero? What is this? By that time, obviously, there was a good understanding of the concept of zero, but it's, if you just saw that, ex nihilo, so to speak, from nothing, is kind of, is that nothing? Is that zero? Is that just nothing? What does it mean there? Cliff comments, if I had 3 ducks and gave them all to you, surely the ancients must have had a concept of what that left me with. Well, I'm sure they said it was nothing. I mean, we know in uh, in the Odyssey, right? There's the story of Odysseus running into the Cyclops and saying, and Cyclops saying, "Who's there?" And at least in the Latin version, I guess it was Nemo. Nobody, nobody is there, and that was sort of a part of the storyline of the Cyclops is telling the other Cyclopses, I'm being attacked by who? By nobody. So, clearly the notion of a nothing was there, but mathematicizing that and saying it's a thing that's a number like 1, 2, 3, that was something that I think took a long time. Let's see. Elsie is asking about what are notable dead-end paths taken in the history of mathematics, science, technology. Well, I mean, there are many things where people sort of had a theory and the theory just turned out to be quite wrong. I mean, I'm thinking of, for example, how does life originate? Well, there's, you have mud and maggots spontaneously arise in the mud. That was a thing people believed for a long time. It turns out, there are maggot eggs probably in the mud, and that's where they come from. There were lots of medical theories that in their sort of raw form are just nonsense. There are lots of theories. One of the things that's so confusing between these different fields is the intuition of what kind of a theory is going to be nonsense and what kind of a theory isn't is very different. I mean, in physics, the simple is usually right. In biology and medicine, usually it's all very complicated. It's more complicated than you can possibly imagine. If there could be a virus involved that was infecting things, there probably is one. If it, whereas, and it's, some sort of tale of what's going on. In physics, if you say, oh, and there are 17 effects that are contributing to this, and that's how it's happening, that's probably not correct. I mean, if we look at modern times, we can see, well, lots of things where people say there's a mystery. Okay, there's a common kind of thing is to say, we've got this thing we observe, but there's 90% of it doesn't seem to do anything. That's been said about the brain. It's been said about DNA. It's been said about mass in the universe, so to speak. It's kind of 90% is missing. That's always a very suspicious claim. I mean, when people say this thing, well, in biology, again, this is this intuition question. In biology, when people say there's this thing, the appendix, the frontal lobes in the brain, all kinds of different things, and they say, oh, that's just useless. That's an accident of biological evolution, and it has no. We don't know what it's for, so it must be for nothing. In biology, that has usually been wrong. That's in other areas where it's kind of like, well, that's an extra detail. It has often been true that extra detail doesn't matter. So I think, the intuition of these different fields is different. But in terms of things where people really kind of got it, where I think there's a couple of different things. Sometimes things were very vague. In antiquity, people discussing atoms versus fluids and so on, it was all rather vague at that time. When things got more precise, people could take a path where it's just outright wrong. And, one that I've been particularly reminded of recently is, what is heat? People thought, heat flows from one object to another. What flows from one object to another? It must be a fluid like water. And so people invented this idea of caloric fluid, which is where, calories and all this kind of, all these kinds of words come from. Caloric fluid was a thing in the early 1800s. And that was, in fact, through the 1800s, that was kind of what heat was assumed to be, was some kind of fluid that seeped into a material that made it hot. Well, of course, what became clear only at the very end of the 1800s, beginning of the 1900s, was heat is really the result of microscopic motion of atoms and molecules and so on. So it was kind of like there was a theory, it was wrong, interestingly, that completely wrong theory generated some completely correct mathematical physics. In other words, things like the second law of thermodynamics were things about energy conservation. These were developed at a time when people believed that heat was caloric fluid. So even though the grounding was completely wrong, the things that got developed on that basis were in fact correct. I have to say, in modern times, I have this strong suspicion that dark matter is kind of the analog in our times of caloric fluid of the past. Dark matter is sort of matter that has a gravitational effect, for example, on the rotation of galaxies, but which we can't see as luminous stars or anything like that. And so the assumption is, well, it's something that makes gravity. And the only thing that makes gravity is mass, and things that have mass are particles. Therefore, dark matter must be particles, and people mount lots of experiments to look for those particles. My own guess is that dark matter, and by the way, you're already confused by the name, isn't matter at all. It's a feature of the structure of space. In fact, ironically, my own current guess is that it is the precise analog of the story of heat. It is what one might call space-time heat, things to do with the detailed microscopic structure of space, the discrete structure of space, that's the thing that is what is producing the effect that we're calling dark matter, being confused by the term matter and so on. So that's an example in recent times of that. I mean, there are lots of these wrong turns. I mean, one I was just reminded of actually yesterday is coronium. So people observed the sun, and they observed that so you can distinguish when you have a luminous body and we have light coming through layers of gas. There are particular frequencies of light that are absorbed by different gases. And there's a characteristic atomic spectrum for a gas which says, oh, is it oxygen? Is it hydrogen? Is it helium? Whatever else. Well, in the case of the sun, what was observed, particularly in total eclipses, was that there was an outer layer of the sun that had a completely different arrangement of spectral lines than had ever been seen before. And people said, oh, it must be a new thing. They called it coronium. Well, it turns out they were, and they thought, it turns out they were quite wrong, that it was actually just gas that was very hot relative to the temperature of the surface of the sun. So the temperature of the surface of the sun, 6,500 degrees, 6,000 degrees, give or take, is centigrade, is that's the sort of luminous thing that we see. But there's other gas outside of the main part of the sun that is this kind of that's part of the corona of the sun, that is a plasma, like fire, so to speak, that has a different, where the electrons have been stripped away from atoms and so on, which has a different set of spectral characteristics. But people didn't know that you could have this plasma that was ended up at a higher temperature than the actual surface of the sun. And so then they assumed that this was a new and different element. I mean, there have been, gosh, there are so many of these kind of wrong turns that have happened. I mean, then there are things where they're just weird experimental results, like N-rays was a type of radiation that just wasn't a thing. I'm not sure what it ended up actually being, but it was just an incorrect kind of experiment. And occasionally there are things that happen where people claim kind of dramatic results, and the results were just, well, either on purpose or by mistake fudged in some way. Sometimes it's not clear what the true story is. Like cold fusion is a good example from when was that? The late 80s, early 90s, where it was claimed that fusion, which is usually something where you need to have, very high temperatures to get atoms to crash into each other hard enough that they overcome the force of repulsion from electrical, from being like electric charges, something where, that happens in the sun, it happens in a hydrogen bomb. People are trying to make it happen in fusion reactors and so on. But the question was, can you make that happen even at low temperatures? And there was this claim that it did happen in palladium, which kind of absorbs a lot of hydrogen, that it sort of absorbed enough hydrogen and it kind of let the hydrogen atoms get close enough that they can undergo fusion. Well, people sort of jumped on this and said, oh, the experiment was done wrong, it's all nonsense. It's not completely obvious to me that there's no effect there. The thing to understand about it's not hard to get a small amount of fusion to happen without having a very high temperature thing. Temperature is kind of the collective energy of all of those molecules bouncing around. But if all you need is a few molecules that are going really fast or whatever, you can have a small amount of fusion rather easily without having in a way where the thing is generally, quotes, cold. So that's a case where sort of the world decided that that's all nonsense. We'll see. These things happen. It happens in both directions. People come up with things which, like, this is a weird effect, and turns out it's nonsense, or this is a weird effect, and it turns out one didn't expect it, but it turns out to be true. Another good example of that is this was a strange one. This is neutrinos coming from the sun. Neutrinos are particles that interact incredibly weakly. Your typical fairly low energy neutrino will go all the way through the Earth without interacting. But in nuclear reactions, neutrinos are produced. So they're produced in the sun, and there's neutrinos streaming towards the Earth from the sun. And back in the 1970s, people were like calculating how many neutrinos should be produced from the sun, given how much energy is being made in the sun. So particular results were got. And then people tried to detect neutrinos in these giant vats of, well, basically cleaning fluid in deep mines underground. They were in deep mines so that they wouldn't be sort of confused by things from cosmic rays that come to the surface of the Earth. By the time you have a mile of rock between you and the thing that your detector, most of those particles have been absorbed out. Only the neutrinos, which can kind of go all the way through the Earth, survive there, so you can look for them. But anyway, people looked for them and they didn't find anything. And for a while, people were saying, oh my gosh, maybe the center of the sun has gone out. It takes 10 million years for a photon to get from the center of the sun to the surface. So it could have been the case that back in 1975, that it was a correct thing to worry about. The sun has gone out in the center. It's only going to be in another million years, the outer parts of it will have cooled down as well, and we're all toast, actually the opposite of toast. We're all freezing. But in any case, so that was a thing where there was a theoretical calculation that was done about how many neutrinos will be produced, and it turned out not to be correct. And I was very suspicious of this calculation right when it was being reported then, because it had a lot of dependence on very detailed questions about how nuclear reactions happen in the sun, and it didn't seem plausible that the results could be known that accurately. But in any case, it was that was one piece of that where it's like, has the sun gone out? Well, no, actually it hasn't. We just got the calculations wrong. And then later on, it was like, well, it's still mysterious. And then it was discovered neutrinos, which were thought to be massless particles like photons, actually have a small mass. And it's really complicated because they don't just have a mass that causes them to have kind of that's kind of just this neutrino, the electron neutrino or the muon neutrino, the three kinds of neutrinos, that each one just has its own mass. They kind of have a kind of mass that lets them mix into other neutrinos. So something that starts in an electron neutrino can turn into a different kind of neutrino, and that can turn into a muon neutrino and so on. And that's a reason why they were not detected. And so that became another complicated story. But I think there are many wrong turns. And I think it's often is the case that another source of wrong turns is when there is a kind of people make an assumption about how things work, and it looks very elegant. And it's like, then it gets sort of into the textbooks and it gets entwined in the whole kind of structure of the field. An example of this is space-time. The idea that space and time are really the same kind of thing and they can get bundled together, which is something that originated in, I think, 1919. Einstein had sort of talked about the relationship between space and time and relativity. But then Minkowski, who was a mathematician and number theorist, was like, oh, I'm used to these forms, mathematical forms in which things are combined together in such and such a way. This is like what space and time look like. They're being combined like, according to Einstein's theory. So we're going to have this notion of space-time and kind of bundle them together. In our modern recent theory of physics, it's pretty clear that that bundling isn't really correct, that it emerges that space and time have common features, but that's not sort of how things start off. So that, I suspect, will be seen as a kind of 100-year wrong turn in the history of how these things are set up. I mean, we could say the same thing, that just a lot of these different things. I mean, another one very close to my interests is the question of the discreteness of space. People had argued since antiquity, is the world continuous or discrete? By the end of the 1800s, it was resolved that yes, matter is discrete. Then it was resolved that light could be thought of as discrete. And at the time, everybody thought space would turn out to be discrete too, but people couldn't kind of make the math work out. And so that languished for 100 years. And, we now finally, I think, in our physics project, we finally understand that space is discrete and how that really works from a sort of mathematical structure point of view. Maybe we'll get some evidence that space is discrete in the next few years. I'm not sure. People were lucky with Brownian motion at the beginning of the 20th century, that was the kind of final evidence that matter is discrete. You could actually see those pollen grains under a microscope getting kicked around by individual molecules of water and so on. I think, let's see, other wrong turns. I mean, my gosh, science is full of these things. I mean, I think that I'll mention a couple more. So another one is well, in quantum mechanics, the enthusiasm for, like, we're going to make computers that work better and they're going to be quantum computers and so on. My guess is that's mostly a wrong turn. The fact that you can think about making computers out of things other than semiconductors, and you can kind of imagine using superconductors and ion traps and all these kinds of exotic physics that are used for what people call quantum computers, those are all a fine idea. But the question of, can you really get sort of this magically faster computation done, I'm deeply skeptical, because what seems to be happening is you get these different sort of threads of history that are pursued in quantum mechanics. But the point is that we, as observers of where we say we want to get the answer from the quantum computer, we've got to take all those threads of history that the quantum computer sort of internally, independently operated with and knit them all together. That's something which in the standard formalism of quantum mechanics is not accounted for. It's just like there is a measurement and then you get an answer and it's just a mathematical operation. It's not something where you say, what's the mechanism by which that happens? And that's something where I think the people have been sort of saying, we're going to make this, we're going to make this, we're going to make a quantum computer, it's going to be great. And it's, and it turns out that they say, but it's mysterious, it's got all this noise, it's got all this decoherence, short decoherence times, all this kind of thing. Things aren't going right, but it's just an engineering problem, we will solve it. I suspect that is not correct, and that there's actually some fundamental physics that kind of impedes that. I mean, okay, I can keep going with all of these wrong turns. Another significant one was about AI. Back in the early 1950s, for example, when electronic computers were first coming in, they were the typical kind of popular newspaper account of an electronic computer was a giant electronic brain. That was kind of the metaphor for computers, and that was the assumption that just as we had bulldozers and things that could automate mechanical work, so similarly we would have computers that would automate mental work, and they were operating like giant electronic brains. That was the assumption. The assumption was it's real soon now we're going to have computers that are just like brains. 1956 was when the first sort of conference on artificial intelligence and the name artificial intelligence came in. Early 1960s, it was kind of like, yes, it's a given thing that there's going to be that computers are going to be able to sort of do human-like things. And I think it's it's something where um, uh, that, but then it turned out, well, actually, it was more difficult than you expected. And finally, now we have most of the things that were sort of the original promise of AI in the 1950s, we pretty much have as of now. Um, but it took a really long time, and there were many wrong turns along the way of people saying it's going to be this. I mean, there were an ironic wrong turn, right turn, wrong turn, I don't know, was what happened with neural networks. I mean, people had known in around 1900, Raman and Kajal had discovered neurons by looking at the anatomy of the brain and knew that there were these long, stringy things that, and that was pretty quickly, people kind of knew that there were, well, they knew that nerves were electrical like things. They knew these were nerve cells. So they knew that the brain was kind of an electrical related organ pretty early on. Meanwhile, by the beginning, the early 20th century, there were all these electrical machines with all kinds of wires and electromechanical switches and so on. So it was kind of a sort of an obvious thing to think, oh, brains are sort of like electrical machines in some way. And then 1943, Warren McCulloch and Walter Pitts wrote their paper about kind of a formalized theory of that, thinking about neural nets as kind of an idealized thing of just sort of idealized wires connected in idealized ways, and connecting that to things like Turing machines and kind of the emerging kind of formal theory of computation. But so they suggested that, and people like von Neumann and so on, who was very much involved in the origination of electronic computers and their design, was like, thought that was interesting. And in the early days, for example, when he was describing kind of how computers should be set up, he was always talking about organs in the computer, like biological organs, not things like gates and so on, as we would today. But in any case, that kind of idea of neural nets, that's going to be a thing. They're kind of like brains. Then by the 1950s, people were starting to build kind of actual devices that were kind of wires and switches and so on, and say, oh yes, we can use this as a detector of, is this an image of a this or a that? Didn't work terribly well, but that was a beginning thing. There were these things called perceptrons, which are basically just like layers of neural nets, simple layers of neural nets. But then it didn't really work. And then actually people I knew, Marvin Minsky and Seymour Papert, wrote this book about perceptrons in which they sort of mathematically proved that perceptrons couldn't do anything interesting. I use air quotes for mathematically proved, because they took a simple case of perceptrons and showed that the simple case of perceptrons was analyzable and couldn't do anything interesting. But then, years went by, and beginning of the 1980s, people coming from neuroscience and sort of revitalizing this kind of idea of idealized neural networks and getting a few things to work. But then, a long period when, people like me, I played with neural nets a bit at the beginning of the 1980s, and it was like, I don't think these are terribly interesting. And it took until 2011, really, before people, through sort of an accident, discovered that yes, neural nets can actually do, deep neural nets that are really hard to train can actually do really interesting things in image processing and so on. And then we had the big surprise in 2022 of ChatGPT and large language models being able to sort of produce fluent text and so on. And these are things where neural nets were very dead for a very long time, and they looked like very much a wrong turn. And then they came back to life again. And it's, this has happened, this happens with some frequency. I mean, there are ideas somehow, and this is a sort of an aesthetic of ideas. I kind of like to feel that there are ideas which will one day be important, and it's inexorable that they'll one day be important. They're types of kind of methodologies for things which, while they may not be, the world may not be ready for them right now, they have a certain elegance and aesthetic quality that makes them sort of inevitably one day significant. And I think it's always a thing that's interesting to try to identify, because I don't know, things I've tried to do in studying sort of simple rules and what they do, I kind of know that these things will be inexorably important because they are just the obvious sort of idealization. They're the obvious ultimate idealization of things. And eventually they will be sort of, they are the upstream version of lots of kind of detailed downstream things. Let's see. I mean, I could go on. Actually, I'm going to mention one more example of a wrong turn, which is this question of what mathematics is. And, people have just done math and figured things out and so on for years. And then end of the 1800s, people said, let's sort of really sort of clarify what mathematics is. Let's try and break it down into its sort of ultimate primitives and say, what kind of a thing is it? And particularly David Hilbert was big on this idea that mathematics is just this kind of formal game in which you have these structures, these axioms, and you can kind of pick them as you want. And then you can build things up based on those formal axioms. And he was famously said, mathematics, where we talk about, planes and triangles and lines and circles and so on, we could as well be talking about tables and chairs and have these axioms that say, whenever two tables are, whenever you have two tables combined with three chairs, you have a such and such. And you just make these arbitrary axioms and kind of build up this sort of arbitrary structure of mathematics on that. Now, that idea of building up arbitrary structure turned out to sort of segue in a rather circuitous way into the idea of computing and the idea of computation and the idea of setting up arbitrary computational rules. That's super important. But the question is, what does this mean for math? Is it really true that math is sort of built of arbitrary axioms? Now, that's a thing where I've studied this quite a bit. It's sort of an interesting thing to ask, what is math like when you sort of take this axiom point of view? I wrote this book about the physicalization of metamathematics that is about kind of the sense in which sort of this structure of all these theorems is kind of like the structure of things like physical space when you take some kind of limit. But I think that this question of sort of what do mathematicians actually do, and are they actually doing these deeply axiomatic things where they're building everything up from grains of sand and building this sort of big tower from that, or are they doing something that's sort of more aesthetic and more kind of like broad brush strokes and so on? And I think this is something that actually matters, because there are people spending a lot of effort sort of trying to axiomatize certain aspects of mathematics, where that is sort of their model for what mathematicians do, and it probably isn't the right model. It's probably a wrong turn. It's closely related. There was a question earlier about set theory. Set theory, which originated with Georg Cantor, it originated in a very pragmatic way about looking at limits of trigonometric series and the convergence, regions of convergence of trigonometric series. But it turned into this field that in its simple form is just, you've got a set of objects and you can say, what's the union of this set with that set if you don't let there be any duplicate objects, or what's the intersection? Those are very simple versions of set theory. The fancier version of set theory involves infinite sets and is full of all kinds of angels on heads of pins, kind of defined in an infinite set where there's, can you make a correspondence between the elements of one infinite set and another? And how do you fit one infinite set into another infinite set? Because, infinity fits into infinity and things like this. And it's very elaborate and very non-human, actually. It's very much like, it very much follows the David Hilbert view of you can just set up axioms and then see their consequences. And I think that's been, if you ask most mathematicians, what's the sort of foundation of mathematics, they'll sort of probably say set theory. A little bit nowadays, they might say things closer to category theory, but they would have said, for a long time, they would have said set theory. And it's, I think that's probably the sort of axiomatic foundations of mathematics on things like that is probably a wrong turn, although a somewhat more technical one than other ones we've been talking about. All right. Well, we should probably wrap up there. Thank you for lots of interesting questions. And I see more that I didn't get to this time, which perhaps I'll be able to get to another time. And thanks for joining me, and bye for now.